Welcome back everybody, Patrick here, and moving on to the next example, we got two limits to solve here. So we got the limit as x approaches 0 from the positive side of 3 over x minus 3 over e to the x minus 1. And then we got the limit as x approaches 0 from the positive side of 3 over x minus 3 over 1 minus e to the x. So notice that they're very similar functions. The only difference between them is that over here we have e to the x minus 1, and over here we have 1 minus e to the x. And even though it's a subtle, small difference, it's actually going to be a very big difference in what the solution is and how we go about the limits. Why I wanted to include both of these examples. So starting with this one over here, what we want to do, notice that first you can't sub in 0 directly because we'd have 3 over 0, which is undefined, and then we'd have e to the 0, which is 1, but then we'd have 1 minus 1, which is 0. Right? So we'd have two denominators that are 0. So we got to go about it a different way. First off, let's figure out what is actually happening to this function overall as we approach 0 from the positive side. So we'll look at each of these functions separately. So let's start with 3 over x. Now, as we approach 0 from the positive side, that's maybe like 0.0001, let's say. So we would have 3 over a very small number, a very small positive number. So we know that this is going to go towards positive infinity. And you can actually graph this as well. 3 over x isn't too bad of a graph to make. It's just 1 over x, the parent function, but vertically stretched by a factor of 3. Notice as we're approaching 0 and x value 0 from the positive side, the function's going towards positive infinity. Right, what we got here. Now this function, 3 over e to the x minus 1, this one's going to be a little bit trickier to deal with. What I actually suggest doing is looking at e to the x separately. Now e to the x looks like this over here. Maybe let's make this a little bit more. Okay, that is e to the x right there. So as x approaches 0, right, notice that we have a point 0 and 1 here. But we're approaching 0 from the positive side. So we're approaching it from the positive side. So notice that we're approaching 1, but from the positive side. So this e to the x, it's going to be like 1.0001. Versus if we're approaching 0 from the negative side, then e to the x would be like 0.999, for example. Right? But we're approaching it from the positive side. The 0 from the positive side. So we got to figure out what's the y value. The y value is going to be approximately this. So what's going to happen is we're going to have 3 over 1.0001 minus 1, which is going to be like 3 over 0.0001. So 3 over a very small positive number, which is going to give us positive infinity. And so from there, we're able to tell that this here is an indeterminate difference. Remember, that's one of the formats. And the reason why you need to get specific like this is you got to figure out, is this going to be positive or negative infinity? Because if this was negative infinity, then this wouldn't be an indeterminate form. And that's actually, just as a heads up, not to spoil the question, that's what's going to happen here when we get to this question. But it's important to go over this preliminary work here to first see whether it's an indeterminate form or not, because sometimes it doesn't have to be. But in this case it is. It's positive infinity minus positive infinity. So we had to really go into detail on that denominator to figure out that it's a very small positive number. But if it was 0 from the negative side, it'd be a very small negative number. Okay, so it's an indeterminate difference, which means we need to go about this some kind of other way. Okay, we can't do this direct substitution. So what we can do is we can actually take this and combine it into one expression. So we can get a common denominator, which notice these are two factors that are totally different. So the denominator would be both of these factors multiplied together. So we would multiply this by e to the x minus 1, which means we have to multiply the top by e to the x minus 1. And then we'd multiply this by x, so we got to multiply the top by x. And then this would be x times e to the x minus 1, like that. And so if we, let's simplify this a little bit. Let's distribute. So we'd have 3 e to the x, then I'll put the minus 3x, and then I'll put that minus 3 at the end, all over x e to the x minus x, like that. Right, so we took this, changed it into one expression. So now what's happening is, notice we still can't do a direct substitution. We can't plug in 0 because we'd have 3. This would end up being 1. 3 times 1 is 3. Minus 3 times 0, which is 0. So we'd have 3 minus 0 minus 3, which would give us 0 up here. And then notice this x would be 0, this x would be 0, which would make the denominator equal to 0 as well. But now notice that it's an indeterminate quotient. So it went from being an indeterminate difference, positive infinity minus positive infinity, to an indeterminate quotient. And so now, because it's in that format, what we can do is try to apply L'Hopital's rule on this. And so what we would do is we would take the derivative of the numerator. So the derivative of 3e to the x is just 3e to the x. The derivative of 3x is just 3, and then the derivative of 3 is just 0. All over, notice here we're multiplying two functions, so we'll have to apply the product rule. So the derivative of x is 1 times e to the x, plus the derivative of, we'd have x times the derivative of e to the x, which is just e to the x. And then this here would be minus 1, like that. And so now if we try to do a direct substitution, notice we're still going to get 0 over 0. Right? This would be 1. 3 times 1 is 3, minus 3 is 0. This would be 1. This whole thing would be 0, but then we have the minus 1. 1 minus 1 would give us 0. So it's still an indeterminate quotient. But what we can do is maybe try to apply L'Hopital's rule again, because notice we keep getting constants here. So we know those constants are going to go away in the next repetition. So if we apply L'Hopital's rule again, let me continue this up here. We'd have the limit as x approaches 0 from the positive side. The derivative of the numerator is 3e to the x, all over, the derivative of negative 3 is just 0, so we don't write that. The derivative of e to the x is e to the x. And then here we're going to have to apply that product rule again, so we'd have e to the x plus x e to the x. And then the derivative of negative 1 is just 0. And then notice here, these two are like terms. So we'll have 3e to the x. This would be 2e to the x plus x e to the x, like that. Right? Yeah. This is like a 1 and a 1 here. These are like terms. And now notice we could do a direct substitution. So if we plug in 0 for x now, notice we'll have 3 at the top, 3 times 1. E to the 0 is just 1. 3 times 1 is 3. All over, this would be 2. And then this whole thing, because of this x here, would be 0. And so the answer is 3 over 2. That is the answer for this limit right there. Right? So what's happening, I don't know how this function looks like, but definitely what's happening is as we approach 0 from the positive side, we're going to be approaching a y value of 3 over 2, and it's going to be a hole there. Right? So it's going to look something like that. I don't know whether it goes up or down, but let's say it's just like this. But what's happening is at an x value 0, it's undefined. We know that. So it's either going to be a whole or an asymptote, but it's actually going to be a whole because it's approaching that value, that y value of 3 over 2. All right, so we took the indeterminate difference, we got a common denominator, changed it to one expression, and then it was an indeterminate quotient. And then we applied L'Hopital's rule from here to here, and then we applied L'Hopital's rule again. And then finally we were able to make a direct substitution for 0, and we ended up getting 3 over 2 as the final answer for that limit. Now let's do the second limit here. So limit as x approaches 0 from the positive side of 3 over x minus 3 over 1 minus e to the x. So very similar function as I mentioned, except this denominator is interchanged. Instead of e to the x minus 1, we got 1 minus e to the x. It's actually going to make a big difference. So the 3 over x, we already talked about how that's going to go towards positive infinity as x goes towards 0 from the positive side. Then we got the minus in the middle, but now let's talk about this 3 over 1 minus e to the x. And as I did before, what we're going to do, let's look at this behavior of e to the x first. So this here is e to the x. As we approach 0 from the positive side, we're approaching 0 from the positive side. Notice that this here, it's going to be a y value of 1, but it's going to be a y value of 1 from above 1, right? So this is going to end up being 3 over 1 minus something like 1.0001. Now, if we are approaching 0, this x value is 0 from the negative side, we'd be approaching this y value of 1, but from the bottom. So it'd be like 0.99 down here, which would change everything. But we're approaching this y value of 1 from the top, so it's 1.0001 here. So what's going to happen is we're going to have 3 over negative 0.0001. So it's going to be 3 over a very small negative number. And so we know that this whole thing is going to go towards negative infinity. And so what's going to happen is this whole thing is going towards negative infinity. And so notice what happens here. That's not an indeterminate difference, because these two negatives turn into a positive. Sorry, we don't have to write two positives. Like that. And then positive infinity plus infinity would give us positive infinity. And so that's the answer for that limit right there. Right? We didn't even have to apply L'Hopital's rule or anything, because we know it's going towards positive infinity because that was not an indeterminate difference. Versus here, when we did that, we ended up getting positive infinity minus positive infinity, which is one of those indeterminate difference forms. Right? So just a subtle change like that changes the limit completely. And that's why I wanted to go over this example, both of these examples, just to show you to be really careful on a test. Make sure that you're doing your quote-unquote due diligence on the function before you get into any of the strategies, before you get into L'Hopital's rule or anything like that. Make sure it's an indeterminate form first. Okay, so graphically, again, I'm not sure how these functions actually look like, but what I do know is that this function, I mentioned this already, as we approach 0 from the positive side, it's approaching 3 over 2. A y value of 3 over 2. It's undefined there. It's going to be a whole. I don't know what's going to happen on the left side, but I know on the right side it's going to approach 3 over 2, this y value of 3 over 2. Versus here, as we approach 0 from the positive side, the function is going towards positive infinity. I don't know what's going to be happening on the negative side, right? We didn't do that, but we know that as we approach 0 from the positive side, the function is going to go towards positive infinity. So there's going to be a vertical asymptote on this side. So notice the difference between these functions. All right, so just be careful. Again, figure out what's happening with the function first, see if it's an indeterminate form, and then you can go from there.